Hello everyone, and welcome to this video on orthogonal bases, or bases. In this video I'm going to assume that you know what it means for a set of vectors from an inner product space to be orthogonal. Right? Remember, that's every pair of vectors in the set is orthogonal, has an inner product of 0. I'm also going to refresh your memory here, but also assume you have seen and what it means for a set to be a set of vectors to be orthonormal. Right? A set of vectors was orthonormal if it was orthogonal, right? An orthogonal set, and on top of that, every vector in the set was a unit vector, right? Had a norm of 1. Alright, so in this video I'm going to define what it means for an orthogonal set to be an orthogonal basis of some vector space, and it's probably pretty obvious. It's in the name. You've seen what a basis of a vector space is before, right? A set of vectors that spans the space and is also linearly independent. So that's the same definition here. I'll also define an orthonormal basis on top of that, as you've seen in previous videos. Again, if you've been following, I hope you have, that anytime the word orthogonal comes up when it comes to maybe a pair of orthogonal vectors or an orthogonal set of vectors, the word orthonormal wasn't far behind. And the same is the case here. And then I'm going to go into a few examples where I'm given a set of vectors from some inner product space. I'm asked to show that this set of vectors is orthogonal, right? That it is an orthogonal basis for the vector space, the inner product space. And then once I've verified that the set is an orthogonal basis, I can then construct an orthonormal basis for that vector space using that orthogonal basis. Okay. So here, definition. An orthogonal basis is a basis for a vector space, namely an inner product space, right? A vector space with a certain inner product defined on it. An orthogonal basis is a basis for a vector space V that is an orthogonal set. Simple as that. So it's a basis, right? Meaning, again, it spans V, right? Every vector in V can be written as a linear combination of the vectors in the set. Also, the set is linearly independent, and what we're going to see later is that every orthogonal set of vectors is going to be linearly independent. Pardon me. So here's some examples. In your Euclidean space under the dot product, right, when the inner product was the dot product, the standard Euclidean inner product. In any Euclidean space, R2, R3, R4, Rn, the standard basis is an orthogonal basis of that space. So the standard basis, this fancy E set here with 1, 0, 0, 0, 1, 0, 0, 0, 1, usually called E1, E2, E3, or I, J, K in some physics texts. This is an orthogonal basis of R3, under the dot product, right, under the standard inner product. Because, right, you already know it's a basis, right? Every vector in R3 can be written as a linear combination of these three vectors. They're linearly independent, right? You can check that as well. Very easy to check that. If you had a linear combination of these equal to the 0 vector, the only linear combination of these three vectors that's equal to the 0 vector would be the trivial combination, where all the scalars are 0, all the weights are 0. And it's an orthogonal basis because it is an orthogonal set, right? If you take the dot product of E1 with E2, it would be 0. The dot product of E1 with E3, it would be 0. And the dot product of E2 with E3, it would be 0, right? So every pair of vectors is orthogonal, right? It is an orthogonal set. Okay. Another example. So the standard bases under the dot product for Euclidean space are examples of orthogonal bases, but it doesn't have to be the standard basis, right? So here the set, say S set of vectors with, from R. These are from R2 with 2 components, right? The vector 4, 2 and negative 3, 6. This is an orthogonal basis of R2 under the dot product. For this video, I'm going to just stick to the standard inner product, for Euclidean space. Just remember, though, that the concept of orthogonality depends on how the inner product is defined. Right? And when the inner product was the dot product, orthogonal basically meant perpendicular, right? In the usual notion of perpendicular, vectors forming a 90-degree angle. So, got 4, 2. Negative 3, 6, right? Again, you can easily show that they form a basis for R2. Right? Every vector in R2 can be written as a linear combination of these vectors. They're linearly independent. Right? The only linear combination of these that would form the 0 vector is the trivial one, right, where the weights are all 0. And they're orthogonal, right? There's only one pair of vectors here. Just and you can see that the dot product would be negative 12 plus 12, which would be 0. Right? So this is an orthogonal basis as well, right? Besides the standard basis for R2. Okay, and if you'd like to see, I'll show you, because I'm working with R2, R3 here, we can actually see pictures of these things, visualize them. And we'll see that under the dot product I mentioned, orthogonal has the same meaning as perpendicular, forming 90-degree angles. Let me show you some pictures of these vectors on the Geogebra site. This is geogebra.org. They have a 2D calculator and 3D calculator. So here's vector 4, 2, right? As starting at the origin, going out to the point 4, 2. Here's vector negative 3, 6. Let me zoom that out a bit. Right? Can you see how they would they look perpendicular here? If I were to rotate this, maybe it's more obvious, but these two vectors do form a 90-degree angle. Right? And under the dot product, orthogonality and perpendicularity, if that's even a word, have the same meaning. All right, so hopefully it's clear to see that these two vectors do form have an orthogonal basis for R2 for the entire plane. Then I have the 3D calculator also, where you just have your standard basis vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 in these black, red, and green colors here. If I zoom in. Now, I'll rotate this so you can see the 90 degrees. Red and black, 90 degrees. Black and yellow, 90 degrees, or black and green, 90 degrees, and green and red vector, 90 degrees, right? So, and they point in 3 different directions in this 3-dimensional vector space R3. So this is an orthogonal basis for R3, right? With the 3 standard basis vectors. Okay. Now, the question that would naturally follow from this, right, whenever you're talking about orthogonal, the word orthonormal usually isn't far behind. So if a basis is orthogonal, the next question would be, hey, is this an orthonormal basis for the space as well? Right, so a very similar definition. Right? An orthonormal basis, orthonormal, is a basis for a vector space or inner product space, right? Because again, the concept of orthogonal and orthonormal depend on the definition of the inner product on that space. So an orthonormal basis is a basis for an inner product space V that is an orthonormal set, right? So again, it's a basis, so it spans V, it's linearly independent, and it's an orthonormal set, right? Meaning that every pair of vectors in the set is orthogonal, their inner product is 0, and every vector is a unit vector, right? In an orthonormal set, every vector has a norm of 1 unit. Okay, so a simple example would be the standard bases for Euclidean space under the standard Euclidean product, under the dot product. So that example I had up earlier, right, with 1, 0, 0, 0, 1, 0, 0, 0, 1, this is an orthonormal basis of R3 as well, right? It's orthogonal and it's orthonormal, right? Because every vector is a unit vector. Right? If you took remember the norm of a vector was the square root of the inner product of that vector with itself. So I mean, if you take the dot product of each of these vectors with themselves, you're going to get 1, right? E1, this with itself is 1, this with itself is 1, this with itself is 1. So, and then the square root of all those would be 1. Right? So every vector is a unit vector. Right? So yeah, so that standard basis vector for R3 under the dot product would be an orthonormal basis. Now that other one I gave you on the previous page, the other example with, for R2, the set S with vectors 4, 2 and -3, 6. This was an orthogonal basis, right? This was an orthogonal basis of R2 under the dot product, but it's not an orthonormal basis of R2 under the dot product. Reason being, right, if you took the dot product of this first vector, 4, 2 with itself, you'd get 20, right, 16 plus 4. And then, therefore, the norm of the first vector, which I'm calling V1, would be the square root of 20, or 2 times the square root of 5. That's not 1. Right? So right away I'm saying, okay, sure, this is an orthogonal basis for R2 under the dot product. But because this one vector, I have found a vector that's not a unit vector, right? Its norm is not 1. This set is not an orthonormal set, so it can't be an orthonormal basis for R2 under the dot product. And you could have also said, hey, V2, this -3, 6, is also not a unit vector, but as long as you find one vector, if you find one vector in the set that's not a unit vector, it doesn't have a norm of 1, then it's not orthonormal. Alright, well the question would be though, hey, this set isn't orthonormal, right? It's orthogonal, right? The dot product of these two vectors is 0. It's orthogonal, but it's not orthonormal. Could I take this orthogonal set and construct an orthonormal basis? And of course, and I've done this in previous videos, if you've been watching, following, I hope you have. It's very easy to take an orthogonal set like this, like S here, and construct an orthonormal set. You just simply need to normalize each vector in the set. And to normalize the vectors in a set, to normalize a vector, you just multiply that vector by the reciprocal of its norm, or divide by its norm if you want to say that. So I've got on this next page, right? And again, I think I've written something like this similarly when we talked about changing an orthogonal set into an orthonormal set. It's the same procedure. So an orthonormal basis can be constructed from an orthogonal basis by multiplying each vector by the reciprocal of its norm, or you could say dividing by its norm. So take that example that I just had, right? The vector 4, 2, and negative 3, 6, this set S, right? We said earlier this is an orthogonal basis of R2, but not, an orthonormal basis. But I could, because it's an orthogonal basis, I could very easily construct an orthonormal basis of R2 by dividing each of these by their norms. Right, now we saw on the previous page what the norms were. Right, the norm of the first vector was the square root of 20, or 2 root 5. The norm of the second vector was 3 root 5. Right? The square root of 45, you take 9 plus 36 and then the square root of that. So I'm going to divide each component by 2 root 5 from V1, and then for V2 I'm going to divide each component by 3 root 5, and these simplify to this. So dividing 4/2 by 2 root 5 gives me this vector, with components 2 divided by the square root of 5 for the first component, and 1 divided by the square root of 5 for the second component. Now you could rationalize these if you wish, but I'm not doing that here. Right. And then this vector, right, negative 3, 6, I divide it by its norm. I divide it by 3 root 5. If I do that for each component, the first component simplifies to negative 1 divided by the square root of 5, and then the second component 2 divided by the square root of 5. This set, which it's not S, so see I'm calling it S prime. Right, it's a different set of vectors, but it came from S, so thus the word, the S is still there, but I'm calling it, S prime, so it's different. This set is an orthonormal basis of R2. Right, so it's a basis for R2, right? Every vector in R2 can be written as a linear combination of these two. They're independent, and the set is now orthonormal, right? It's orthogonal. The dot product of these two vectors would be 0, right? These two vectors are orthogonal, and now each vector is a unit vector, and you can double check that. Right? Find the norm of this first one and the norm of this second one, and both of them would have a norm of 1. And let's take a look at these. All right, I've got them on, again, back on the Geogebra site. So here was, V1, V2, that was 4, 2, and negative 3, 6, an orthogonal basis for R2. Here's 2 root 5, 2 divided by the square root of 5, 1 divided by the square root of 5. Now do you see it's in the same direction? All right, it's really tiny here. But you see it runs in the same direction as V1, but now it's normalized, now it's just a unit ln. And then V4 here I've got, is negative 1 divided by the square root of 5, 2 divided by the square root of 5. See, it's running in the same direction as the green vector, but it's normalized. It's now just a unit ln. So let me get rid of these first two. And here, and you see they still form this 90-degree angle, right? We're still using the dot product here, so orthogonal means perpendicular. See, they're forming 90-degree angle, and basically these two vectors are just the vector 1, 0, and 0, 1, just kind of rotated, counterclockwise a bit. Right? Because it's just like 1, 0, and 0, 1, but tilted a bit, right? Rotated by a small angle. Right? So this is orthonormal basis. Right? And the reason we would like an orthonormal basis for a particular inner product space is because expressing vectors as linear combinations of orthonormal vectors is actually quite simple. And I'll have a video coming up after this. I'm not going to do that in this video, where I talk about writing the coordinates of a vector relative to an orthonormal basis, and an orthogonal basis too, but orthonormal is very nice when it comes to writing coordinates, as you'll see in my next video, but not now. All right. Okay. Now, what I'm going to be doing in the for the examples in this video, what I'm actually going to do, ones that I'm actually going to work out, I'm going to want to show that a given set of vectors is an orthogonal basis of a certain inner product space. So I'll need some results. I need some theorems to help me out. I'm not going to write out the proofs of these theorems, right? That's not the point of this video. But I do have some important results regarding orthogonal sets and orthonormal sets right here. So this is the relationship between, orthogonal sets and linear independence. All right. So this first statement, if I have a set of vectors from some inner product space V, if a set of vectors from an inner product space is an orthogonal set, right? Orthogonal, meaning every pair of vectors, right, has an inner product of 0. If S is an orthogonal set of non-zero vectors, right? So all these V1 through Vn that I've got here are non-zero. Then the set will be linearly independent. All right. So very nice to know that, right? That if you have an orthogonal set of vectors, that set will be linearly independent. Okay. Now, notice I mentioned the word non-zero here, right? Because if any of these was the 0 vector, then it would be dependent, right? I hope you recall that from maybe a section on linear independence of vectors you've come across. I'm assuming you've come across that at this point. By this point, if a set contains the 0 vector, it's going to be by definition a dependent set. All right, so but an orthogonal set of non-zero vectors always going to be linearly independent. And that's wonderful. And then some things follow from this. So if a set of orthogonal vectors, or orthogonal non-zero vectors, is independent, well then S would be considered an orthogonal basis for the span of S. Remember, the span of S was the set of all linear combinations of the vectors from S. So S definitely spans the span of S, right? That's the definition of the span of S. And we've just said that if it's an orthogonal set of non-zero vectors, it's independent. So S would be considered an orthogonal basis for the span of S. And then if you'd like an orthonormal basis for the span of S, right, the vector space, the span of S, just divide each vector by its norm. That's what I've got here. So S prime, which is just every vector from the orthogonal set S divided by its norm, would be an orthonormal basis for the span of S. Right? And then a very, very nice result. And then this one actually comes from we've seen this result before when talking about bases for other just general vector spaces. If you have a set of vectors that's linearly independent, and the number of vectors in that set is the same as the dimension of the space, right? If it's a vector space whose dimension you already know, then you have a basis for that space. Right? So if the dimension of a vector space is n, right, and I have n vectors in my orthogonal set, then S would be a basis for V, an orthogonal basis for the vector space. Okay. All right. Because remember, every vector space, every basis of a vector space of a finite dimensional vector space, every basis of a vector space has the same number of vectors. Okay. All right. So keeping that in mind, right, that every orthogonal set of non-zero vectors is independent, and if it has the same dimension if it has the same number of vectors as the dimension of a vector space, then that orthogonal set will be an orthogonal basis for that vector space. Okay. So I have just two examples, right, to finish the video, but they'll probably take a while. What I'm asked to do is I'm going to be given a set of vectors from some inner product space, and I'm going to be asked to first show that this set of vectors is an orthogonal basis for the vector space. Then, if it is, and it should be, right, I'm saying show that it is, then construct an orthonormal basis for that same space from set S, right, using set S. Alright, so show that S equals, I got this set of three vectors from R3, 1, 2, 1, 2, 0, negative 2, negative 4, 4, negative 4. Show that this set of vectors is an orthogonal basis for R3 under the standard inner product, right? And again, usually if the inner product isn't mentioned, you can assume that they mean that they're using the dot product if it's Euclidean space, right? The standard inner product or the Euclidean inner product. All right. Well, first I'll just show that it's an orthogonal set. All right. So I'm going to call these vectors in my set here v1 through v3, right? So 1, 2, 1. Call that vector v1. 2, 0, negative 2. I'm going to call that vector v2. Negative 4, 4, negative 4. I'm going to call that vector v3. And if I want to show that this is an orthogonal basis for R3 under the standard inner product, I'm going to first show that it's an orthogonal set, right? Because you can't be an orthogonal basis unless you are an orthogonal set. All right. So let's check the pairs then. What's the inner product of vector 1 with vector 2? Now again, remember this is the inner product is the dot product. So I'm just going to write dot product from here on out, but just know that that's the way the inner product is defined here. All right, so that would be one, again, how inner product works, right? Dot product works is you multiply corresponding components and then add those products, right? So 1 times 2 plus 2 times 0 plus, and then 1 times negative 2. That's 2 plus 0 minus 2, which would be 0. All right, so vectors v1 and v2 are orthogonal. And I can remember I kind of wrote it's like the perpendicular symbol is shorthand for, I can use a shorthand for orthogonal here. But that's not all, right? I have to show that every pair of vectors is orthogonal to show that the set is orthogonal. So how about, that was v1 with v2, now v1 with v3. So again, I'm just going to write dot product this time, but this is the inner product, right? So it's the dot product of v1 with v3. So again, 1 times negative 4 plus 2 times positive 4 plus 1 times negative 4. And that would be negative 4 plus 8 would be positive 4 plus negative 4 would be 0. So vectors v1 and v3 are orthogonal as well. But that's not all, right? There's still one more pair to check, and that would be v2 and v3. And of course, the larger the set of vectors, the more pairs you need to check, right? So v2 with v3, almost the dot product, the inner product here of v2 with v3, that'd be 2 times negative 4, the first components, plus 0 times 4 for the second components, and then the product of the third components, negative 2 times negative 4. So this is negative 8 plus 0 plus 8. That's 0. Wonderful. So v2 and v3 are orthogonal. Right? So every pair of vectors in this set is orthogonal. So S S is an orthogonal set of non-zero vectors, notice, right? None of these vectors is the zero vector in R3. So S is an orthogonal set of non-zero vectors. Well, by the result that I just showed you on the previous page, if this is a set of, if it's an orthogonal set of non-zero vectors, well then the set is a set of linearly independent vectors. Therefore, S is linearly independent. All right. And since the dimension of R3, right, we're trying to show that this is a basis for R3. Since the dimension of R3 is known to us, right, we know the dimension of R3 is 3. And S has 3 vectors, right? And S is, an independent set of 3 vectors. That's the key, though, that they have to be independent, right, to be a basis. And S is an independent set of 3 vectors, which is the same number as the dimension of R3 that we know. Then S is a basis, right? S is a basis for R3. And putting this all together, we showed S is an orthogonal set of 3 independent vectors. So and the dimension of R3 is 3. So S is a basis for R3. It's an orthogonal set that is also a basis for R3. Therefore, we could call this an orthogonal basis for R3. Putting all that together. Therefore, S is an orthogonal basis for R3. And again, I'm not mentioning the dot product, but just when I don't mention it, just assume I mean under the standard inner product, under the dot product. Wonderful. Now the second part of this problem, right, other than showing that the set was an orthogonal basis for R3 under the standard inner product, was, then after I've shown this, construct an orthonormal basis for R3 from S, right? So using these same vectors. So next part, let's construct an orthonormal basis for R3, under the dot product. So remember what I said before, right? This is simple. I have an orthogonal set already, an orthogonal basis for R3. I simply need to find the norms of these vectors and multiply by the reciprocal of the norm, or divide by the norm. All right, so again, hopefully easy enough. So what's the norm of vector 1? Remember, the norm of a vector is the square root in an inner product space is defined as the square root of the inner product of that vector with itself. And the inner product here is the dot product. So this is the square root of, the dot product of v1 with itself. So that'd be 1 times 1 plus 2 times 2 plus 1 times 1. 1 plus 4 plus 1, the square root of 6. So notice that's not 1, right? So that's not a unit vector. So this is not an orthonormal basis already, right? It's just orthogonal. So I'll divide this first vector by the square root of 6, right? And what's the norm of vector 2? And same thing, it's the square root of, the dot product in this case, right? The inner product is the dot product of that vector with itself. So 2 times 2 plus 0 times 0 plus negative 2 times negative 2, right? So 4 plus 0 plus 4, that's the square root of 8. Or if you'd like to simplify that, right? 2 times the square root of 2, right? Square root of 4 times square root of 2. Again, not a unit vector, right? So I actually do need to divide this second vector by the square root of 8. And then the norm of the third vector, again, the square root of the dot product of this vector with itself. So that'd be what? 16 plus 16 plus 16, the square root of 48, which is 16 times 3, so 4 times the square root of 3 if you want. Right? But again, none of these are unit vectors, but we're going to make them into unit vectors, or we're going to normalize them, right, by dividing by the norms, right, multiplying by the reciprocals of the norms. So an orthonormal basis for R3 would be the following. So say, again, I'll call this S prime, right, not S, because it's not going to be the same three vectors, right? We're dividing them by some number, equals, 1 divided by the square root of 6 times the first vector. And then if you'd like, you can put this in and say this is 1 divided by the square root of 6, 2 divided by the square root of 6, 1 divided by the square root of 6. But I'm just going to write it like this, okay, with the scalars on the outside. That's v1 normalized. And then, 1 divided by the square root of 8, or 1 divided by 2 root 2, right? That was the norm of the second vector, times the vector 2, 0, negative 2. There's, and again, if you want to put this in, you'd get, 1 divided by the square root of 2, 0, and then negative 1 divided by the square root of 2. But again, I'll just leave it like this for now. And then the last one was, 1 divided by the square root of 48, or 1 divided by 4 root 3, times the vector negative 4, 4, negative 4. And if you'd like, again, you can put this inside, make this negative 1 divided by the square root of 3, positive 1 divided by the square root of 3, negative 1 divided by the square root of 3, right, would be, the third vector normalized. This is an orthonormal basis for R3. Right? It's orthogonal, right? The set's orthogonal, and now every vector is a unit vector. Is an orthonormal basis for R3, right? Under the standard inner product, right? Under the dot product. And let's take a look. Let's take a look at these. Again, these are from R3, so we can actually visualize them. I got again the Geogebra website here with some three-dimensional drawing. So back to the 3D calculator, back home here. Now, these were the standard basis vectors, right? That's an orthonormal set. You saw that earlier, right? That's an orthonormal basis for R3. Let's get rid of those. Now the vectors I had from S were 1, 2, 1, that blue vector that just showed up, 2, 0, negative 2, right? That black vector pointing down below the plane, and the vector negative 4, 4, negative 4, right? Now, I said already that this is an orthogonal basis, right? These three vectors point in three different directions, but they do form 90-degree angles, right? We're talking about the dot product here, so orthogonality is perpendicular. And I'll show you. Right, you can see that the red and the black vector form a 90-degree angle. The red and the blue vector are forming a 90-degree angle, and the blue and the red vector are forming a 90-degree angle. Right, you can probably see that after all that. So these three vectors are forming an orthogonal basis for R3. But then I just found their unit vectors, right? I normalized them. So remember, I multiplied the first one by 1 over the square root of 6, the second one by 1 over the square root of 8, and the third one by 1 over the square root of 48. So let me put those vectors up. Black, red, and blue. And they're pointing in the same directions as these three. Let me just get rid of these three now. And now I have an orthonormal basis, right? I'll zoom in a bit here. And they're pointing in the same directions as the first three, but now they're all a unit long. They're all a single unit long. So these three vectors are basically like the standard basis, just rotated a bit, moved somewhere else, rotated somewhere else. Because the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 also form an orthonormal basis, right? But they're just pointing in different directions. But they form 90 degree. See the 90-degree angle there, the 90-degree angle there, red and black, red and blue, 90-degree angle. Right. So yeah, wonderful. All right. Okay. And again, the beautiful thing about an orthonormal basis will be when we talk about writing the coordinates of vectors relative to these bases. So again, that's in an upcoming video. All right. So my final example is again the same thing, same kind of example, but this time in a different inner product space. Not Euclidean space, not R2 or R3. And with a different inner product, right? Not the dot product. All right, just to show you something else. So here I have the same kind of problem. Show that this set of vectors, and again, it's just three vectors. Not every example is going to have a set of three vectors. You could have a set of 2, 4, 5, whatever. Just I'm just showing you some with 3. So show that this set S. So this is a set of polynomials, right? About 1x and x squared minus a third are three polynomials, three vectors from the vector space P2, right? Remember, P2 is the set of all polynomials of degree 2 or less. What I'm asked to do is show that this set of three polynomials is an orthogonal basis for P2. Right, meaning that every polynomial in P2 can be written as a linear combination of these, and they're independent, and they are also orthogonal under this inner product, with the inner product being that standard integral inner product, but from -1 to 1. Right, so say the inner product of two polynomials will be the integral from -1 to 1 of the product of those polynomials with respect to x. Alright, and then after I've shown you that this set of vectors, this set of polynomials, is an orthogonal basis for P2, then I'll find their norms, right, the norm of each vector, and use those to construct an orthonormal basis for P2 from S. Alright, so again, call these vectors V1, V2, and V3. Right? So the polynomial 1, that's V1. Polynomial x is the second vector. Polynomial x squared minus a third is the third vector. Okay. And if I want to show that it's an orthogonal basis for P2, I'll first show that it's an orthogonal set, just like the last example. So let's look at each pair. Right? Is each pair of vectors in this set orthogonal? Right? Is the inner product 0? So what's the inner product of V1 with V2? Right, so again, not the dot product this time, right? It's a totally different space, different inner product. This will be the integral from -1 to 1 of 1 times x. Right? Remember, this is 1 and this is x. Right? So 1 times x, or just x with respect to x. Now this is 0. Right? This is 1/2. You could have said that this is an odd function, and you're going from negative a to a, -1 to 1. This is going to be 0. But this is 1/2 x squared, right? From -1 to 1, and you plug in 1, plug in -1, you get the same value, then subtract them, you're getting 0. Okay, so polynomial vectors v1 and v2 are orthogonal. Now again, orthogonal here doesn't necessarily mean perpendicular, because really you can't really picture this space so much. Now I mean, P2 is isomorphic to R3. So if you translated things to coordinates relative to R3, maybe you could have a picture of a vector in R3 that represents a polynomial in P2, but that's beside the point. Right? So they're orthogonal, V1 and V2. Alright, so that was one pair. Now how about V1 and V3? So again, this is the integral from -1 to 1 of, v1 is 1 times x squared minus a third. So that's just x squared minus a third, right, with respect to x. Alright, so antiderivative, right, that'd be 1/3 x cubed minus 1/3 x. And we're going from -1 to 1. And can you see that when I plug in 1, getting 0? When I plug in -1, getting 0. I'd get 0 minus 0 here, which is 0. So vectors v1 and v3, so the polynomial of 1 and x squared minus a third are orthogonal in this inner product space. Great. But again, that's not all. Right? I got one more pair to check, v2 and v3. Right, so this would be the integral from -1 to 1 of x times x squared minus a third, which if you distribute, that would be x cubed minus 1/3 x. Alright, that's x times x squared minus a third. And again, I have the same case as I had in the first pair. Right? This is an odd function from -1 to 1. This is going to be 0. Alright, I'll just say this is 0, and you can double check that if you wish, do the antiderivative and all that, but it's 0. So v2, the polynomial x, and v3, that polynomial x squared minus a third, are orthogonal. And those are the only pairs of vectors I can see in this set of vectors here. I've checked every pair. Or every pair of different vectors, right? That's what it means for a set to be orthogonal, right? Every pair of different vectors is orthogonal. Okay, so we see now that this set S is an orthogonal set of non-zero vectors, right? None of these polynomials is the zero polynomial, or just 0 in P2. So S is an orthogonal set of non-zero vectors, right? That's key, that they're non-zero. So by that result I mentioned to you earlier, the theorem earlier, since this is an orthogonal set of non-zero vectors, then S must be linearly independent, right? So those are linearly independent vectors. And we're trying to say that this is an orthogonal basis for P2. And this is a space that you know the dimension of, right? Again, if you've been following, watching my videos, it's come up many times now. The dimension of the vector space P2 is 3. Right? Remember the standard basis had polynomials 1x and x squared. It had 3 vectors. And set S is an independent set of 3 vectors. Which is the same number as the dimension of the space. So S is a basis for P2. And we showed earlier that it's an orthogonal set, right? It's an orthogonal set that is also a basis. So therefore, S is an orthogonal basis for P2. Wonderful. All right. So I've just verified that this set of polynomials, 1x and x squared minus a third, is an orthogonal basis for P2 under the the standard integral product, right? The integral inner product. Now let's construct, right? Then construct an orthonormal basis for P2 from S. So let's go through here and let's find the norms of each of these vectors, right? So now it's using this using S here. Now let's construct an orthonormal basis for P2, okay, under this inner product, right? Again, if I don't mention the inner product, it's under the inner product that was stated earlier, right? Okay, so this will involve, right, just finding, normalizing these vectors, finding the norms, right? So what's the norm of V1? Remember, this is the square root of the inner product of V1 with itself. Right. So V1 is the polynomial 1. So this is the square root of, and then the inner product of V1 with V1 would be the integral from -1 to 1 of 1 times 1, 1 squared, or just 1 dx. Now, this one's pretty easy, I think, right? This integral would just end up being 2. So this is the square root of 2, which notice that's not 1. All right, so this vector, this 1, is not a unit vector under this inner product. I would need to then divide this by the square root of 2 to get a unit vector under this inner product. Okay, do the same thing for the rest, right? What's the norm of vector 2? Again, it's the square root. I'll just do square root of the inner product of x with x, right? V2 is x. The integral from -1 to 1 of, the inner product of x with x would be, just the integral from -1 to 1 of x times x, or x squared, with respect to x. And again, this one, you do 1/3 x cubed, plug in 1, plug in -1, subtract them, you get in 2/3. So this is the square root of 2/3, which, I can write Now, because I'm doing the reciprocal, I'll put the square root on the top. Be the square root of 6 divided by 3. If I multiply the top and bottom there by square root of 3. So what I'm going to do now is multiply x by 3 over the square root of 6, right, the reciprocal of this, to get a unit vector, right, because this is not 1. X is not a unit vector under this inner product. So I'm going to multiply by the reciprocal of the norm. All right, and then what's the norm of V3? And that's the square root of the inner product of V3 with itself, which will be the integral from -1 to 1 of, x squared minus a third squared. Alright, so I'm going to do this integral off to the side. Do this integral separately. So that'd be the integral from -1 to 1 of x to the fourth, minus 2/3 x squared plus a ninth. Alright. And then doing the antiderivatives here, this is 1/5 x to the fifth minus 2/9 x cubed plus 1/9 x. And we're going from -1 to 1, which is really just going to be double what I get when I plug in 1, right? Because this is odd here. So this is going to be 2 times 1/5 minus 2/9 plus 1/9. No, -2/9 plus 1/9 is a fifth minus a ninth. And it's 2 times a fifth minus a ninth. Which would be 2 times 9/45 minus 5/45. That's 4. So 2 times 4/45. That's 8/45. So we're getting the square root. The square root of 8/45, which, that's 2√2 in the numerator, 3√5 in the denominator, right? Square root of 45. And like I said, I'm going to be multiplying by the flip of this. Actually, maybe I should do this instead, right? So put the radical in the denominator, so when I flip it, it's in the numerator. So if I took this and multiplied the top and bottom by square root of 2, it'd be 2 over the square root of 6. Same thing. All right. And then here I'll do the same thing where I have the radical and I'll rationalize the numerator. So multiply the top and bottom by the square root of 2, that'd be 4 in the numerator, over 3 times the square root of 10. All right. Yeah. All right, and I'm going to multiply vector v3 by the reciprocal of this, right, to normalize it. So after all that, we get our orthonormal basis for P2 under this inner product. All right. So here was S. Let me back this up. Sorry. So here was S. 1x and x squared minus a third. So, again, I'll call this S prime because it's not S. It is the set of these polynomials from P2. So remember, the norm of 1 was the square root of 2. Right? The norm of 1 was the square root of 2. So I multiply by 1 over the square root of 2. Right, so 1 over the square root of 2, or square root of 2 divided by 2 if you like rationalizing. There you go, times 1. There's 1 over the square root of 2, or square root of 2 over 2. This is a unit vector under this inner product. Next, take x and multiply by the reciprocal of its norm. Right, its norm was 2 divided by the square root of 6. I multiply by the reciprocal, that'd be the square root of 6 divided by 2. So the square root of 6 divided by 2, and then times x. This polynomial is a unit vector under this inner product. And finally, taking x squared minus a third, multiplying it by the reciprocal of the norm. Its norm was 4 divided by 3 root 10, so I multiply by 3 root 10 over 4. So 3 root 10 over 4 multiplied by x squared minus a third. All right, if you want to distribute that, that's cool too, but that polynomial is from P2, and this polynomial, this 3 root 10 over 4 times x squared minus a third, this is a unit vector under this inner product. This set of these three vectors, these three polynomials, is an orthonormal set basis for P2. All right, the first one was just orthogonal. Now it's both orthogonal and orthonormal. Right, every polynomial is a unit vector now. Is an orthonormal basis for P2. And again, when I say for P2 and don't mention the inner product, I mean under that inner product that was mentioned, right? That integral inner product. All right, so lots of stuff there. All right, lots of stuff going around. So yeah, just know the definitions, right? Know what it means. First of all, you have to know what it means to be a basis of a space, right? You have to span the space and be linearly independent. What does it mean to be an orthogonal set of vectors, right? Every pair of vectors is orthogonal, their inner product is 0. What does it mean to be an orthonormal set of vectors, right? It's an orthogonal set where every vector is a unit vector, has a norm of 1. And I think probably the key thing coming out of this video was that statement that an orthogonal set of non-zero vectors was linearly independent. This statement here. I think this page was probably the most important page in the video. All right. So if you have an orthogonal set of non-zero vectors, that set will be linearly independent, and therefore be an orthogonal basis for the span of that set. And if you were to divide each vector by its norm, you get a new set that's an orthonormal basis for the span of S. And if you ever come across a vector space with the same number of, or the dimension of the vector space is the same as the number of vectors in your orthogonal set, well, then that orthogonal set will be a basis for the vector space. Great. All right, so I hope this was informative. Hopefully it was easy to follow. And I do hope you enjoy practicing problems of this nature, right, where you're testing for the orthogonality of a set or orthonormality of a set, and whether or not it's a basis for a particular inner product space. Right, thank you for watching.